Hi, and welcome to TEMEKO. In the previous chapters, we learned about damping and how it affects any object in motion. More importantly, we learned that damping is often expressed as a damping ratio based on that value, whether it's less than 1, 1, or greater than 1. The response of a body in harmonic motion varies quite dramatically. In case you don't remember, I have got 5 words for you: under, over, and critically damped. See? I'm sure that worked like a charm. When you are all caught up with those damping-related terms and you understand the physical meaning of damping, there is still something missing. Something we haven't learned yet. See, the thing is, we know how damping works and how it feels, but do we know how to calculate damping? We know that a system with damping will probably undergo less amount of vibration. But how do we know if the system is critically damped, over-damped, or under-damped? How do we estimate the value of the damping ratio? As we have learned before, damping is generally expressed in terms of damping ratio or damping constant. However, it's not easy to derive the numerical value, and it's more frequent that experimental results are used for estimating damping. In another video, we will take a look at how to set up those experiments. For now, let's imagine that we did those experiments and got some nice results. These results are nothing more than the vibration response of the system under study. Now theoretically, assuming that it is an underdamped system, the response equation will look something like this. xt equals c times e to the power minus zeta times omega n times t times sine omega d times t plus phi, where x is the position of the studied point at time t, omega d is the vibration frequency, phi is the phase, and c times e to the power zeta times omega n times t is the amplitude of the movement, which depends also on the damping ratio zeta. The response looks quite similar to a system without damping, except for one key difference, the exponential part. The equation shows how the response decreases exponentially with increase in time, which gives the following envelope. For such a case, we can use the logarithmic decrement to identify the damping ratio. Well, it's pretty easy to obtain the logarithmic decrement. First, we obtain the ratio of 2 consecutive amplitude peaks, and then by taking the natural logarithm of that amplitude ratio, it will give us the logarithmic decrement, delta. For systems where damping is small and vibration decreases slowly, it's a good practice to use multiple periods of time for more accurate results. Then, the equation becomes delta equals 1 by n log natural xt divided by xt plus n times t, where n is the number of periods under consideration. So for the case below, n equals 3. Once you have the logarithmic decrement delta, the damping ratio can be calculated as zeta equals delta divided by square root of 4 times pi square plus delta square. Apart from this method of calculation, there are some rule of thumb values for estimating damping ratios as well, especially because damping is not straightforward to determine in the dynamic systems without measurements, and some practical scenario might not be so experiment-friendly. Some examples presented as percentage of overshoot, that is, how far it oscillates around its equilibrium position, are steel structures, for example, a single piece of shaft of steel, 0.1 to 1% damping. If the structure has bolted joints or shrink fits, etc., something which has friction involved, damping is higher, about 1 to 2%. For rubber dampers, which is a common application in vibration isolator, 5 to 20% damping. For oil-lubricated journal bearings, using oil, 20 to 30% damping. For shock absorbers, which are designed to dampen vibration, 40 to 100% damping. Well, it was not that difficult, right? We learned one way of estimating damping using logarithmic decrement from an experimental response. Then we learned some intelligent rule of thumb values for estimating damping for certain material and practical scenarios. In the following videos, we will learn how to set up the measurement device for calculating damping using frequency response function and half power points. It's going to be awesome. See you soon.